Yeah. So, dear students, welcome back after the break. So, we are talking about composite transistor, and what we said is that if we have amplifier, particularly multi-configuration amplifiers, where two transistors are having different configuration or maybe the same configuration, then the analysis can be done slightly smarter way. And to do that, what you can do, two transistors together, we can consider a single one. Say for example, you do have Q1 and Q2 together, where Q1 its collector is connected to supply VDD, and its emitter it is directly connected to transistor 2, and then at the emitter we may or may not be having this bias current. And then the second transistor collector we can consider it is say collector of the composite structure, and then emitter of Q2 it can be considered as emitter of the composite structure. On the other hand, base of the Q1 transistor it can be considered base of the composite structure. So, with that, the whole thing, the shaded portion, if I consider one transistor, and then if you find its small signal parameter, and then we can use this transistor for two configurations, say common collector configuration and then common emitter configuration. So, the moment you make this composite structure in CC configuration, then what will be getting CC followed by CC configuration we can get. So, likewise, if the composite structure or composite transistor, if you connect in CE configuration, then we can get CC followed by CE configuration. Okay. So, let us try to see that how we are getting it. Say we do have the basic composite structure here, whether we do have this bias circuit or not. If we connect the circuit in say CE configuration. So, which means that the emitter we can connect to ground, and at the collector we can put a bias resistor RC connected to VDD supply, and so we can call this is the output port, and at the base we can connect maybe RB, providing the bias current for Q1, base bias current for Q1, and then we can feed the signal there with a meaningful DC. So, what is this circuit configuration we are getting is that, so what we are doing is that composite structure we are making in CE configuration, and then internally if you see that this stage it is coming in CC configuration. On the other hand, this stage it is in CE configuration. So, CE configuration for composite transistor resulting as CC followed by CE. So, likewise, if you consider say the CC configuration. So, now let me consider CC configuration. So, we can connect maybe a bias current here or maybe a resistor, and let you call this is output. Since this is CC configuration, the collector may be connected to supply directly, and at the base will be giving the signal, maybe directly or maybe through a capacitor with bias arrangement, but whatever it is, we do have the input coming to the base of Q1 and output we are observing at the emitter of Q2. So, that makes the composite transistor in CC configuration, and that results into, say, first stage it is CC configuration, and then the second stage is also in CC configuration, which means that if we connect the composite transistor in CC configuration, we are eventually getting CC-CC configuration. Now, how do we then analyze this circuit? As I said that either you can consider the entire circuit and then analyze, and then maybe the better way or smarter way, what we can do, the entire composite structure you can translate into single one. So, if I say that entire circuit equivalently it is working as one transistor, where the collector we call C superscript C, emitter it is E superscript C, and then base is B superscript C. Then whenever we like to get say performance of the corresponding amplifier coming out of this composite transistor, first thing we need small signal parameter. So, what are the small signal parameter? So, beta of the transistor, then R naught, collector to emitter resistance, then transconductance, and then base to emitter resistance R pi. And just to consider this set is parameters of the composite transistor. Let me put the superscript C here for each of the parameter. And then we can find the expression of each of these parameter in terms of the internal and the parameters of the internal or constituent transistor, namely Q1 and Q2. So, in the next slide we will be having that. So, here we are enlisting the small signal parameter, and they are given in terms of the small signal parameter of the constituent transistors, namely Q1 and Q2. So, how do you get that? If you draw the small signal equivalent circuit of the entire circuit, so say for Q1 we do have say GM into VBE of transistor 1, and then we do have the R pi of transistor 1. So, this node it is the base of the composite transistor. Now, here this is connected to DC, we do have, so this is connected to AC ground, and we may or may not be considering this R naught of transistor 1. So, this is connected to AC ground, and then the, so this is the model of Q1, and then we do have the model of the Q2. So, Q2 we do have R pi 2, and then we do have voltage dependent current source GM 2 multiplied by the VB 2, and then we do have the RO of transistor 2, and then finally, we do have the emitter terminal, and this is the emitter of the not only Q2, but the composite transistor. And here we do have the collector of Q2 which is also collector of the composite transistor. So, externally we do have these 3 terminals, and then internally whatever the components are there. Now, if I call this entire structure as one transistor, then we can translate this entire circuit into equivalent one transistor, and then whatever the voltage we do have here at Vc to V, that is VBE. And then from the collector to emitter, whatever the current is flowing, that is GMC multiplied by this VBE. And then collector to emitter, whatever the resistance we do have, that is called ROC. So, if I draw the equivalent circuit of the composite transistor, so we do have GMC multiplied by the corresponding VBE, namely VBEC, and then we do have ROC. So, this is emitter, and then we do have R pi, and this R pi is R pi of the composite transistor. So, here we do have base, and then we do have the collector, right. And if I compare say this equivalent circuit with the whatever the circuit is given here, then first thing is that the resistance from the collector to emitter, it is directly coming from this RO2. So, that probably we can say that ROC is equal to RO2. So, that is the first thing. And then, so this is very straightforward to get. Then next one, it is if you see the beta of the transistor, which means that the current gain if I consider we do have some base current is flowing, and then whatever the current is flowing through the collector to emitter, which is beta C times this IB. So, that gives the corresponding beta of the composite transistor. Now, if I am having say IB of the composite transistor flowing here, IB, so that is eventually same as IB of transistor 1. So, the current flowing through this emitter, which is 1 plus beta 1 times this IB, and eventually that is giving us the base current of the second transistor. So, this current if I multiply with beta of the second transistor, then I will be getting the IC. So, this IC, it is 1 plus beta 1 times IB 1 times beta 2, and that is the ICC. So, if I take this ratio of ICC and IB 1, whatever we do have, which is 1 plus beta 1 multiplied by beta 2, that is what the beta of the composite transistor. So, that is how we are getting the expression of the beta. So, now likewise, if I see the base to emitter resistance, let me use different color. Yeah. So, to get the R pi C, if you look into this circuit, we do have R pi 1 coming in series with this resistance. but then this resistance it is working as emitter degenerator for Q1. So, whatever the resistance we can see, effect of this R2, it is 1 plus beta times of transistor 1 multiplied by R pi 2. So, the impedance at the base 2 with respect to its emitter, it is R pi 1 in series with 1 plus beta times R pi 2. So, that is why we do have R pi c equals to R pi 1 plus 1 plus beta 1 times R pi 2. This part of course, it is not really playing any role to define R pi c. And once we have this R pi c, next thing it is getting the GM, just we have to take a ratio of the two. So, if I take a ratio of the two, then we are getting the corresponding GM. In fact, the GM you can get it through different approach also. You will be converging to this only. So, how do you get the GM alternatively? If I consider this is the VBE, entire VBE, it is from here to here, and part of it, it is appearing here as VBE 2, and this VBE 2 after multiplying with GM 2, it gives the collector current. So, effectively I can say that the GMC, this GMC, it is essentially GM 2 multiplied by whatever the fraction of the VBEC coming as VBE2. And what is this fraction? We do have an impedance here, and also we do have an impedance here, and this impedance is R pi 2, and the impedance here, if you see this part, ignoring this part that you can ignore. So, we can say that and that impedance is R pi 1 in parallel with 1 by GM 1. So, the fraction we are getting here, it is R pi 2 divided by this resistance plus R pi 2. In fact, if you simplify it, you will get the same expression here. Okay. So, anyway, so what you can say that from this equation, we can say that GMC, it is slightly smaller than GM 2. I should say it is slightly, if you see the equation. And most important thing is that this resistance, it got increased, and also the beta of the transistor, it is basically product of beta of the two transistors. So, I should say the main advantage of going for this composite structure is basically improving the beta and then increasing the resistance, while maintaining the GM almost the same and maintaining the R naught almost the same. So, that is how we can probably you can consider the you can get the small signal parameter, and then utilizing those small signal parameter, you can find the gain of CE and CC. So, in the next slide probably we can discuss that. Yeah. So, let you go one by one. Let you consider say CCC stage, which means that this composite structure we can connect in CE configuration. So, to make this circuit in CE configuration, let me connect RC here and then to the supply, and the emitter we can make it to ground, and then at the base we can put a bias resistor called RB connected to VDD, and then you can feed the signal. So, that gives us the internally that gives us the CCC circuit. So, we call this the output. Now, we know that the circuit, it is actually this composite structure, it is in. So, this is whole transistor, it is in CE configuration, and for CE configuration what are the expressions of the different parameters or the voltage gain, namely which is GM multiplied by RC in parallel with R naught. And with GM now we have to consider? We have to consider GMC, GM of the composite transistor. So, likewise RC anyway it is external. So, likewise R naught, it should be R naught of the composite transistor. So, now we do have the expression of the R naught C, which is R naught of transistor 2, and then we do have the expression of GM C. So, this it can be well approximated by say GM 2. So, I should say it is GM 2 multiplied by R C in parallel with R O 2. In fact, this is very much of course, with a minus sign here. Sorry, I forgot that. There is no surprise if you see this circuit. The primarily what we obtain the voltage gain we are getting from the second stage, coming from the Q 2, and Q 1, since it is connected in CC configuration, its voltage gain it is approximately 1. So, that is how we can directly get the voltage gain. Now, the input impedance on the other hand, so for CE configuration input impedance is R B in parallel with R pi, and in this case which R pi? This should be R pi of the composite transistor, and expression of the R pi it is given here. Okay. So, that is the expression of the R pi C. So, you can get its value, and likewise output R O, it is output resistance R O, it is R C in parallel with R O of the composite transistor, and eventually this is same as R O 2. So, we can say that this is R C in parallel with R O 2. So, that is how we can get the performance expression, namely the output voltage and output resistance and input resistance and the voltage gain of the CCC configuration. So, likewise if you connect the circuit in CC configuration, you can find the corresponding the voltage gain, input resistance and output resistance. So, let us see how we are getting it, or probably you can try yourself, and you can connect the circuit in CC configuration. So, to connect the circuit in CC configuration, you can directly connect this to VDD. You can probably connect a bias circuit here, bias current source, and then this is the output port, and then we can connect a bias circuit here R B, and then you can feed the signal here at the base of the composite transistor. And we know the voltage gain, it is approximately 1, and then input resistance. So, in case if we have some RL connected here, then the input resistance of the composite structure, it is R B in parallel with whatever the resistance we do have, which is R pi of the composite transistor in series with 1 plus beta of the composite transistor multiplied by R L. Now, again we do have the expression of R pi C and then beta C, it is given here. So, from that you can find the expression of the input resistance. It may be observed that this part, impedance of this part, it is in fact it is quite high, and in presence of this R B, of course, this R B it may be dominating that. So, if you are constructing this circuit with this R B, you may not be really seeing much change, but internally the circuit input resistance it is quite high. So, on the other hand, output resistance R O, we can approximate this by 1 by G M, and this is 1 by G M C, and this is given by 1 by G M 2. Okay. So, I should say this is approximation. Okay. So, that is how we can analyze the CCCE and CCCC configuration using composite transistor concept. Now, let us move to MOS based circuit. In fact, okay, sorry, before we go to the MOS circuit, we do have one more information to we like to share. We have talked about the CCCE stage. Sorry, we have talked about CCCE stage, and so if I consider this composite structure and then if I connect this transistor in CE configuration, then we are getting basically the CCCE configuration. And what is its main advantage? The input resistance it becomes quite high. Instead of connecting the circuit in this way, there is a smarter way where instead of connecting this Q1 collector of Q1 to VDD, even if you are connecting this to the output, then also we can get the input resistance, it is quite high. So, that connection, whatever the connection just now we are showing, that gives us a different configuration, it is referred as Darlington pair. So, this Darlington pair, I should say it is kind of modified version of CCCE stage. Why I am sharing this information? Because this Darlington pair it is frequently used for operational amplifier, later we will discuss, which is commonly known as op amp, to increase the input resistance of the op amp. So, you may be surprised that then why we do have a special kind of configuration, why not CCCE configuration. As I said that it is on principle they are both the configurations are same except this connection. So, I should say this kind of modification it gives us the Darlington pair. Okay, now, let us move to the MOS circuit. Similar to BJT based different basic configuration, we can also summarize the performance matrices of the common source, common drain and common gate configuration coming out of MOS transistor. So, these are the three basic configurations, and for each of these configurations we have enlisted qualitatively we have enlisted different performance matrices, namely voltage gain, input resistance, output resistance, input capacitance and then current gain. So, here again it is I should say most of the information it is very similar to whatever we have seen for BJT, except this CC stage, its input resistance it is very high, as you know that gate to source connection it is through insulator. So, we can say that it is almost infinite theoretically. So, and that is the only difference. As a result, we may not be requiring any special circuit to increase the input resistance of the CS stage, but then to decrease the output resistance of CS stage, we can use the common drain amplifier to decrease the output resistance, mainly because if you see here the common source amplifier, it is a very good voltage mode amplifier, but main concern is that its output resistance is high, and of course, its input capacitance is also high. And this problem, the output resistance, since it is high, that can be avoided or rather that can be managed by using common drain stage cascaded with that. So, we can say that common source we can connect with common drain to get a better, or I should say lower output resistance. In fact, that also helps to improve the input capacitance. Later we will see that, so we should say that this configuration it is very similar to whatever the common emitter followed by CC stage. So, in the next slide we will be just summarizing its performance, particularly the common source followed by common drain amplifier. Yeah. So, here we do have the common source. So, we do have the common source amplifier followed by common drain stage. Note that the drain the next stage the second transistor gate, it is directly connected to the drain of transistor 1. That is because it is very convenient, and not only that, it first of all we do not require any capacitance here. Second thing is, if you are putting a capacitor here, then you need to have separate bias at the gate, and but then whatever the DC voltage it is available at the gate of transistor 1, that may be sufficient to bias the second transistor, and hence it is directly getting shorted. So, this CC rather CS CD amplifier, if you see its main advantage is that the output resistance. So, output impedance, it is, I should say, 1 by GM of the second transistor, and input resistance, of course, here we do not have any, rather this input resistance is infinite. So, R in it is eventually coming from the bias circuit only, R 1 in parallel with R 2, and then we do have of course the voltage gain, which is coming from the CS stage, and that is GM of transistor 1 multiplied by R 3 in parallel with R O of transistor 1. And this stage, the second stage, of course, its gain it is approximately 1. So, its voltage gain it is essentially coming from the first stage. Yeah, so this mixing of the two configurations, it is primarily to get the lower output impedance. In fact, we can also have similar kind of mixing, namely the CES and CG. As I said that CS and CE, they are the heart of the amplifier, and then to have connection with other circuit, we need to take help from buffer. So we'll be we are in this case we are taking help from common drain to reduce the lower to reduce the output resistance. Likewise, if the common source stage, it is cascaded with common gate, we will be getting some other advantage. Particularly, that helps to boost the gain. So, that configuration we can say that common source followed by common gate for this is for MOS family, and likewise common emitter followed by common base, which is for the BJT family. And both of these two circuits, their purpose is primarily to increase the gain of whatever the gain of the common source or common emitter amplifier we do have. So, that topic, of course, that is also multi configuration, mixing multi configuration, that will be discussed in the next class. So, let me then summarize whatever we have discussed today in three parts of this this lecture today. It is first we have started with motivation of mixing different configuration, and then we have discussed about utilizing the CC stage to decrease the output impedance, and that is done for both cases, C followed by CC and then CC followed by CC. For both the cases, output impedance it has been decreased. Then we also have discussed how to use the CC stage, common collector stage, to increase the input impedance. So, here we are the first CC stage, it is helping to increase the impedance of the main one. So, either it may be CC or CE, and then also we have discussed about something called a special configuration, Darlington Pair, which is quite popular, but that is I should say on principle it is same as CC followed by CE. And then also we have just now we are talking about the decreasing output impedance using the common drain amplifier for MOS family. So, if we have say a common source amplifier, we can cascade with that common drain, and that gives us a lower output impedance. In fact, here these two and then here all are pure BJT. On the other hand, this is pure MOS circuit. There is a possibility of mixing the MOS and BJT to make the multi-transistor configuration. And so, say for example, if we have say common source amplifier, we can connect this common source amplifier with common collector. So, this is MOS. So, this is MOS transistor based, and then this is on the other hand BJT, right. And the purpose it is same. By now, I think you will be able to correctly guess that CC stage it helps to reduce the output resistance. So, likewise we can connect say CE stage preceded by or maybe followed by common drain. To get the, so this is BJT and this is MOS, and like that we can have common emitter preceded with common drain amplifier. So, if you do this, the input impedance, it will be increased by this common drain. So, that is how we can mix the BJT configuration along with MOS configuration, provided the situation helps you to do so. We, as I said, that we yet to cover numerical examples, either in the next class or next to next class we will be talking about, depending on the situation. I think that is all we need to cover today. Thank you for listening.